Welcome to ElectroTunes CEWP Transformer Construction. A simple-to-winding transformer construction consists of each winding being wound on a separate soft iron limb or core which provides the necessary magnetic circuit. This magnetic circuit, known more commonly as the transformer core, is designed to provide a path for the magnetic field to flow around, which is necessary for induction of the voltage between the two windings. However, this type of transformer construction, where the two windings are wound on separate limbs, is not very efficient since the primary and secondary windings are well separated from each other. This results in a low magnetic coupling between the two windings as well as large amounts of magnetic flux leakage from the transformer itself. But as well as this O-shaped construction, there are different types of transformer construction and designs available which are used to overcome these inefficiencies, producing a smaller, more compact transformer. The efficiency of a simple transformer construction can be improved by bringing the two windings within close contact with each other, thereby improving the magnetic coupling. Increasing and concentrating the magnetic circuit around the coils may improve the magnetic coupling between the two windings, but it also has the effect of increasing the magnetic losses of the transformer core. As well as providing a low reluctance path for the magnetic field, the core is designed to prevent circulating electric currents within the iron core itself. Circulating currents, called eddy currents, cause heating and energy losses within the core, decreasing the transformer's efficiency. These losses are due mainly to voltages induced in the iron circuit, which is constantly being subjected to the alternating magnetic fields set up by the external sinusoidal supply voltage. One way to reduce these unwanted power losses is to construct the transformer core from thin steel laminations. In all types of transformer construction, the central iron core is constructed from a highly permeable material made from thin silicon steel laminations. These thin laminations are assembled together to provide the required magnetic path with the minimum of magnetic losses. The resistivity of the steel sheet itself is high, thus reducing any eddy current loss by making the laminations very thin. These steel transformer laminations vary in thicknesses from between 0.5 mm to 0.5 mm, and as steel is a conductor, the laminations and any fixing studs, rivets, or bolts are electrically insulated from each other by a very thin coating of insulating varnish or by the use of an oxide layer on the surface. If you found this video helpful, consider subscribing to our channel for more informative content. Transformer construction of the core. Generally, the name associated with the construction of a transformer is dependent upon how the primary and secondary windings are wound around the central laminated steel core. The two most common and basic designs of transformer construction are the closed-core transformer and the shell-core transformer. In the closed-core type core form transformer, the primary and secondary windings are wound outside and surround the core ring. In the shell-type shell-form transformer, the primary and secondary windings pass inside the steel magnetic circuit core, which forms a shell around the windings as shown below. Transformer core construction. In both types of transformer core design, the magnetic flux linking the primary and secondary windings travels entirely within the core with no loss of magnetic flux through air. In the core-type transformer construction, one half of each winding is wrapped around each leg or limb of the transformer's magnetic circuit as shown above. In the core-type transformer construction, one half of each winding is wrapped around each leg or limb of the transformer's magnetic circuit as shown above. The coils are not arranged with the primary winding on one leg and the secondary on the other, but instead half of the primary winding and half of the secondary winding are placed one over the other concentrically on each leg in order to increase magnetic coupling, allowing practically all of the magnetic lines of force go through both the primary and secondary wind. However, with this type of transformer construction, a small percentage of the magnetic lines of force flow outside of the core, and this is called leakage flux. Shell-type transformer cores overcome this leakage flux as both the primary and secondary windings are wound on the same center leg or limb, which is twice the cross-sectional area of the two outer limbs. The advantage here is that the magnetic flux has to closed magnetic paths to flow around external to the coils on both left and right-hand sides before returning back to the central coils. This means that the magnetic flux circulating around the outer limbs of this type of transformer construction is equal to phi-2. As the magnetic flux has a closed path around the coils, this has the advantage of decreasing core losses and increasing overall efficiency. Warning: our videos may cause excessive learning and excitement. Subscribe at your own risk. The type of wire used as the main current-carrying conductor in a transformer winding is either copper or aluminium. While aluminium wire is lighter and generally less expensive than copper wire, a larger cross-sectional area of conductor must be used to carry the same amount of current as with copper. So it is used mainly in larger power transformer applications. Small kVA power and voltage transformers used in low-voltage electrical and electronic circuits tend to use copper conductors, as these have a higher mechanical strength and smaller conductor size than equivalent aluminium types. The downside is that when complete with their core, these transformers are much heavier. Transformer windings and coils can be broadly classified into concentric coils and sandwich coils. In core-type transformer construction, the windings are usually arranged concentrically around the core limb as shown above, with the higher voltage primary winding being wound over the lower voltage secondary winding. Sandwich or pancake coils consist of flat conductors wound in a spiral form and are so named due to the arrangement of conductors into discs. Alternate discs are made to spiral from outside towards the center in an interleaved arrangement, with individual coils being stacked together and separated by insulating materials such as paper of plastic sheet. Sandwich coils and windings are more common with shell-type core construction. Helical windings, also known as screw windings, are another very common cylindrical coil arrangement used in low-voltage, high-current transformer applications. The windings are made up of large cross-sectional rectangular conductors wound on its side, with the insulated strands wound in parallel continuously along the length of the cylinder, with suitable spacers inserted between adjacent turns or discs to minimize circulating currents between the parallel strands. The coil progresses outwards as a helix resembling that of a corkscrew. The insulation used to prevent the conductors shorting together in a transformer is usually a thin layer of varnish or enamel in air-cooled transformers. This thin varnish or enamel paint is painted onto the wire before it is wound around the core. In larger power and distribution transformers, the conductors are insulated from each other using oil-impregnated paper or cloth. The whole core and windings is immersed and sealed in a protective tank containing transformer oil. The transformer oil acts as an insulator and also as a coolant. Your support means the world to us. Subscribe, comment, and share our videos to help us grow. Transformer.orientation. We cannot just simply take a laminated core and wrap one of the coil configurations around it. We could, but we may find that the secondary voltage and current may be out of phase with that of the primary voltage and current. The two coil windings do have a distinct orientation of one with respect to the other. Either coil could be wound around the core clockwise or anti-clockwise, so to keep track of their relative orientations, dots are used to identify a given end of each winding. This method of identifying the orientation or direction of a transformer's windings is called the dot convention. Then a transformer's windings are wound so that the correct phase relations exist between the winding voltages, with the transformer's polarity being defined as the relative polarity of the secondary voltage with respect to the primary voltage as shown below. Transformer dot orientation. The first transformer shows its two dots side by side on the two windings. The current leaving the secondary dot is in phase with the current entering the primary side dot. Thus, the polarities of the voltages at the dotted ends are also in phase, so when the voltage is positive at the dotted end of the primary coil, the voltage across the secondary coil is also positive at the dotted end. The second transformer shows the two dots at opposite ends of the windings, which means that the transformer's primary and secondary coil windings are wound in opposite directions. The result of this is that the current leaving the secondary dot is 180 out of phase with the current entering the primary dot. So, the polarities of the voltages at the dotted ends are also out of phase, so when the voltage is positive at the dotted end of the primary coil, the voltage across the corresponding secondary coil will be negative. Then the construction of a transformer can be such that the secondary voltage may be either in phase or out of phase with respect to the primary voltage. In transformers, which have a number of different secondary windings, each of which is electrically isolated from each other, it is important to know the dot polarity of the secondary windings, so that they can be connected together in seriesating. Secondary voltage is summed or series opposing the secondary voltage is the difference configurations. The ability to adjust the turns ratio of a transformer is often desirable to compensate for the effects of variations in the primary supply voltage, the regulation of the transformer, or varying load conditions. Voltage control of the transformer is generally performed by changing the turns ratio and therefore its voltage ratio, whereby a part of the primary winding on the high voltage side is tapped out, allowing for easy adjustment. The tapping is preferred on the high voltage side as the volts per turn are lower than the low voltage secondary side. The result of all this insulation is that the unwanted induced eddy current power loss in the core is greatly reduced, and it is for this reason why the magnetic iron circuit of every transformer and other electromagnetic machines are all laminated. Using laminations in a transformer construction reduces eddy current losses. The losses of energy, which appears as heat due both to hysteresis and to eddy currents in the magnetic path, is known commonly as transformer core losses. Since these losses occur in all magnetic materials as a result of alternating magnetic fields, transformer core losses are always present in a transformer whenever the primary is energized, even if no load is connected to the secondary winding. Also, these hysteresis and the eddy current losses are sometimes referred to as transformer iron losses, as the magnetic flux causing these losses is constant at all loads. Copper losses. But there is also another type of energy loss associated with transformers called copper losses. Transformer copper losses are mainly due to the electrical resistance of the primary and secondary windings. Most transformer coils are made from copper wire, which has resistance in ohms, omega. This resistance opposes the magnetizing currents flowing through them. When a load is connected to the transformer's secondary winding, large electrical currents flow in both the primary and the secondary windings. Electrical energy and power, or the I to R losses, occur as heat. Generally, copper losses vary with the load current, being almost zero at no load, and at a maximum at full load when current flow is at maximum. A transformer's VA rating can be increased by better design and transformer construction to reduce these core and copper losses. Transformers with high voltage and current ratings require conductors of large cross-section to help minimize their copper losses. Increasing the rate of heat dissipation, better cooling by forced air or oil, or by improving the transformer's insulation so that it will withstand higher temperatures can also increase a transformer's VA rating. Then we can define an ideal transformer as having no hysteresis loops or hysteresis losses give zero. Infinite resistivity of core material giving zero eddy current losses give zero. Zero winding resistance giving zero I to asterisk our copper losses give zero.